This presentation is a short overview of photographic and motion video compression theory as it has evolved over the last 50 years, starting with the digital fax, which first appeared around 1960, and ending with the newly developed ZPEG motion video algorithm. A three-step framework is used to explain and compare the various technologies. The first step is a lossless conversion of frames into an intermediate format suitable for a second step which will introduce loss into the video. Two loss-inducing techniques are in common use: reduction in the resolution of the image and division of the intermediate data by a scaling factor called a quantizer. A final third step generates the actual compressed representation using a Huffman table. An early single-frame picture compression algorithm is used by fax transmission. An intermediate resolution is created by taking the difference between scan lines of the image. Loss is introduced by resolution reduction. A single Huffman table is used to perform the final compression. Here we see two consecutive lines scanned from the image. The difference between these adjacent lines is taken. Loss is introduced by reducing the resolution of the line. Huffman compression is driven by a fixed table known to both compressing and decompressing sides. The MPEG algorithm also employs a differencing technique between frames instead of between lines. The frame to be compressed is divided into segments, and a search is made to find the best matching segment in an earlier frame. The vector to the best match and the difference between the blocks jointly form the intermediate representation. The difference, or error term, is quantized by a single fixed value. A single fixed Huffman table is then used to perform the final compression. The motivation for MPEG compression is the intuitively attractive idea that video is comprised of objects moving from frame to frame. Here are two consecutive frames showing a woman moving slightly against a background of trees, also moving slightly. If we imagine a decomposition of the source frame into segments to be used to comprise the target frame, we will discover the limitations of this conceptual model. The perspective view of our model as seen by the camera has changed so dramatically that no good fit exists between the frames. The concept that the computer can efficiently determine the location of objects traveling through frames is belied by the actuality that objects rotate. Objects discover and hide background. Objects change in size. Objects change lighting. Frames are inherently noisy. Even perfect matches have error, so very expensive searches are needed in order to have confidence we have the best match. There is no good theory to compress the difference terms. These factors limit MPEG's ability to compress video. JPEG uses a frequency-based transform to represent a video frame. The resulting subbands are individually processed with a quantizer value tuned to that particular subband. The final compression step is once again performed with a single Huffman table. The decomposition of a full resolution frame is illustrated here. Successive subband partitions can be combined to return a successively higher resolution representation of the original frame. Each of the individual subbands of the decomposition corresponds to a particular visual frequency. A human visual system model is used to derive the optimum quantizer value for that frequency, the value that removes exactly the content to which the human eye is insensitive. 64 quantizers are individually applied to each of the 64 subbands. ZPEG differs from JPEG in that it represents multiple frames of video in a single three-dimensional transform. Each subband is individually quantized, analogously to JPEG. An adaptive Huffman compression technology is applied to the final compression step. The decomposition of 8 frames creates 512 subbands. Each subband has distinct spatial and temporal frequencies. A human visual system model is used to specify quantizers which remove the content to which the human eye is insensitive. These quantizers optimally remove redundancy within the frame and that which exists between frames. Let's recap and reorganize the many concepts we have discussed in the last few minutes with a short overview of the historical compression roadmap, a summary of the design principles underlying each technique, and a summary of the performance resulting from the implementation of those principles. Our compression roadmap starts with the differencing-based fax transmission, which dominated still image transmission for 30 years. The next advances JPEG, the first transform-based compression algorithm, and provides optimal single-frame compression to this day. The first multi-frame compression standard is MPEG. MPEG is based on conventional differencing techniques harkening back to FEX technology. The limitations of frame differencing give rise to a strategy of bandwidth reduction through reduction of visual quality. ZPEG breaks the compression barriers suffered by MPEG and is even capable of providing optimal degraded video performance over extremely narrow bandwidth lengths. 3 important design criteria are the number of quantizers tailored to remove redundant information, the number of Huffman tables used to compress the result, and the symmetry of the compression operation as compared to the decompression operation. JPEG still image compression produces ideal results with its 64 quantizers, while MPEG's differencing strategy is limited to only 1. ZPEG uses 512 quantizers, which optimally remove information within and among frames. JPEG uses a single predefined table to perform Huffman compression, as does MPEG. ZPEG uses multiple tables, chosen based on the statistical behavior of the video sequence being compressed. JPEG is a symmetric algorithm, requiring no more computational power to compress than to decompress a frame. MPEG requires typically thousands of times more power to compress, making it unsuitable for real-time or teleconferencing operations. ZPEG, as a transform-based algorithm, requires no more power to compress a video sequence than it does to play the video sequence back.